I want to talk a little more about how we follow acid-base titrations at not just the equivalence point. So when we're dealing with following titrations, we talked about this idea that there would be indicators that we could use for the equivalence point, right? And this idea that we need to have a change in a property of our solution, a drastic change when we get to the equivalence point. And so, what is changing as we're going along, as we're going through here? We know we eventually will reach that equivalence point, and what we really want to track is pH, right? If you start with an acidic solution and you add a bunch of base to it, you hit the equivalence point when all the acid is gone, and so your solution switches from being acidic to being either neutral for a split second, but then basic is what you're going to hit. And so we want to be able to track and monitor the progress of a titration by using pH. And so when we're following out like the idea of monitoring a titration, we know we start with, say, our acid in a flask and we're slowly adding base. And so as the titration progresses, it would be measuring or adding some volume of base. So this would be something along the lines of time or progress of the titration, and pH will change in response to what we are doing, how we have added, how much base we have added to our solution. So let's do the titration of 0.2 molar HCl with NaOH. So the HCl is going to be in our flask, and I am adding the NaOH from the burette drip drop into my HCl solution in the flask. So what's going to be the pH that I start with? Well, initially, what's in the solution? And I'm looking at the solution in the flask, so that's going to be HCl. So I start with HCl, which is a strong acid, which means I know that the concentration of hydroniums is equal to the nominal concentration of HCl, whatever I designed the concentration to be, so 0.2. And the pH is the negative log of that hydronium concentration. So unsurprisingly, I have started with 0.2 molar of a strong acid. The pH is quite low at 0.87. So it starts out certainly as an acidic solution. So what's the pH at the equivalence point going to be? So what is in the solution? Well, I know equivalence point is when I'm doing my reaction. And the equivalence point is defined as where the moles of base added, so the moles of NaOH, is equal to the moles of HCl that I started with. So if there are equal amounts of reactants, they have perfectly reacted. There is no HCl and no NaOH in solution anymore because they are perfectly reacting. There's no limiting reagent, nothing's left over because they're equal the same. All I have are products, especially because this is a strong acid, strong base. I react to completion, so I just primarily have water and NaCl. That means NaCl is not an acid or a base, so that is water and salt. The pH is going to be 7. This is generally true for the equivalence point of the titration of a strong acid and a strong base. It does not matter what you start with, which strong acid, which strong base, or what order you do it in. For the equivalence point, you will always perfectly react that strong acid and base to make water and a salt that does not affect the pH, and the pH will be 7 at the equivalence point. So this is how we can define where the equivalence point is whenever we're doing the titrations of strong acid and strong base. So what happens if we keep going past the equivalence point? We just keep adding in NaOH. Well, all of the HCl is gone, right? The equivalence point was where all of the HCl was gone. So if we just keep adding NaOH, it's just adding base to this solution, right? We're just adding, we functionally have created water at the equivalence point. We basically have salt water. And so if we keep adding base, we're adding base to salt water. So that's going to become the dominant acid or base in solution. And we're just going to end up with a high pH. So we just make a base solution. We just end up with a really high pH out past there. So if you just keep going way past the equivalence point. What about in between all these points? What about what's going on in between? So we can kind of reason what's happening initially, what's happening at the equivalence point, and what happens well beyond that. But we want to kind of know what's the shape of the line. I'll tell you right now, it's not a straight line. So what is the shape going to be? So what we can do is pick a point, plot it out, and see what's going on. In the titration of 55 milliliters of 0.2 molar HCl, what is the pH after 15 milliliters of 0.30 molar NaOH has been added? So if I want the pH of a solution, I know that that's the negative log of the concentration of hydroniums. That's always going to be, so when I'm asked for what's the pH, I really want to know what's the concentration of hydroniums. And so the question is, what's in the solution? What's going to potentially create hydroniums? Well, I've added HCl, right? I know that was in the solution initially. That's a strong acid. NaOH is also in solution. That's sodium and hydroxide. That's a strong base. So those are going to react with each other. So normally, we look at like how does everything affect water, do the water stuff. But if you have a strong acid and a strong base, those are going to react with each other first. And then whatever's left over, that's going to affect the water and the pH of the water. So let's see how that goes.
All right, so I got this titration where I'm not at the equivalence point, and I want to know what the pH is. So I started with 55 milliliters of 0.2 molar HCl, and I'm adding in some NaOH. So one of the things that we want to be mindful of is this is a different setup of the previous titrations where we didn't know what the concentration was. Here we do know the concentration of what's in the flask, right? The 0.2 molar HCl is what's in the flask, and we just want to know the pH along the way. And we want to kind of figure out what's going on here. So one of the first things we want to think about is, the chemistry that's actually happening here, right? What is the actual reaction? So we know we have HCl reacting with NaOH. So we have an acidic solution reacting with a basic solution. We know these are kind of the overall what we put into the solution, but the chemistry in there, we probably have some hydroniums. These ions are floating around separate from each other, but we can still predict the reaction based off this. We know the acid, the hydrogen part, would react with the base, the OH part. So that would produce water plus NaCl. And so, when you only have HCl or you only have NaOH, we can figure out the solution based off that, the pH based off that. But here we're going to be doing some actual chemistry. And the question is, how much of each of our of what we're dealing with do we have? How many moles do we have present? You'll note this is not an equilibrium problem where we need to use an ice table because this is a strong acid reacting with a strong base. This is very, very product favored. This reaction goes very, very far to completion. We can just use stoichiometry. So we don't actually want the molarities or the concentrations. We want the actual moles. We want to get the actual moles of things, of each of our reactants that are present. So we'll go through that process. We'll start with, we want to get moles of HCl. And so I have, 55 milliliters, 0.0 milliliters. I'm going to get that into molarity, so I know it's 1,000 milliliters per 1 liter. And then 0.20 moles of HCl per 1 liter. That's just using the molarity. Instead of using the molarity equation, I'm going to use molarity as a conversion factor between moles of solute and liters of solution. And so that tells me I have 0.011 moles of HCl. For NaOH, similarly, I have 15.0 milliliters. Convert that into liters, divided by 1,000, and then use the molarity of that, which is 0.30 moles of NaOH per 1 liter of solution, giving me 0.0045 moles of NaOH. So I'm just taking my volumes that are in milliliters, I'm converting each of them to liters, and then using the molarity to convert to moles of solute in those solutions. So I've got that representation now here, what that looks like. And so one of the things we can see is that these amounts, I have different amounts of my two reactants. So I can write that out. I have 0.011 moles of this and 0.0045 moles of this. And we know it's going to be a stoichiometry problem. Because these are strong acids and strong bases, we don't need to worry about an ice table. We don't need to worry about an equilibrium mixture. This is going to go all the way very far to reactants. So this becomes a stoichiometry problem. If you remember, when we have a stoichiometry problem with two different amounts of reactants, that is a limiting reagent problem. These are going to react until one of them runs out. The coefficients are 1 on each of these, right? This acid-base chemistry, we have 1s all across the board. And so what ends up happening is one of these will run out, and it's just going to be the lower amount. So this is going to react completely. You're going to lose all of this. And because it's a one-to-one stoichiometry, that amount is going to be lost over here. So we can do these limiting reagent problems dealing with acid-base chemistry kind of in a similar concept to doing an ice table, except we don't need to worry about X. Here are my initial amounts. What's going to happen is they're just going to react completely with whatever the lower amount is. So it's not an X because it's not equilibrium. I know how much it's going to shift. All of this is going to react, and it's going to react the same amount of my other reactant, leaving me with no NaOH and 0.0065, whoopsies, 0.0065 moles of the HCl. If we look over here, we can also predict the moles of H2O and NaCl, but H2O is neutral, so it doesn't affect the pH. NaCl, it's not an acid, it's not a base, so again, doesn't affect the pH. If these were acids or bases, we would need to account for those, and don't worry, we'll deal with that later. But for now, we just don't need to worry about this part because these are the only things that can affect the pH. So all the NaOH reacts, which we expect, because it's the limiting reagent. So we started with a lot of acid. We added a little bit of base. We now have all the base is gone, and we just have less total acid. So this is the total moles of acid that are present in the solution. Okay, so that's on the right track, but we still want to know the pH. So our equation for pH is that it's equal to the negative log of the concentration of hydroniums. So what I have is that I have 0.0065 moles of HCl. That's a molarity. This is a raw moles. So I need to take this and turn it into a molarity, which means I need to divide by the volume. And we want to be careful here as to what exactly the volume is. We can see we started with 15 milliliters. We have added, 55 milliliters. We have added 15 milliliters of solution. So in the process of adding the base into the acid solution, we've also added a bunch of extra solvent. What we can do is we can make an approximation that the total volume is going to be equal to the sums of those smaller volumes. So 55 milliliters plus 15 milliliters. Oh, I forgot to get the point zeros on all those. 70 milliliters. Note, volumes are not generally additive. If you add pure water to pure water, it is additive. And these concentrations are relatively low. If you were adding like 8 molar HCl to like 4 molar NaOH, this would not work. But we don't do titrations with such concentrated acids and bases because those are just gnarly reactions. And so because these concentrations are low, this sort of approximation is going to work out. You'll also notice this is 3 sig figs, but you'll note our moles is only 2. And basically, that's going to be okay. This is probably, making this approximation is probably wrong to 1 sig fig. It might be like 69.8 milliliters or 70.2 milliliters or something like that. And so since we're going to go down to 2 sig figs when we make our molarity anyway, not really a big concern. Or it's going to get washed out, right? The error in this approximation is going to get washed out by the error in this measurement. So what I can finally do, the concentration of HCl after the reaction is done, I have less HCl because some of it has reacted, and I have more volume. I have more volume because it has, I've diluted it functionally by adding in all the solvent that was carrying the base. This should be liters. So, whoopsie. 6.5 moles HCl divided by 0.0700 liters. We want to actually get a molarity, not divide by milliliters, get some crazy number. And we get 0.093 molar. And that's the concentration of HCl. This is the concentration of HCl. And so there's kind of 2 effects when we do the titration. One, the concentration, the actual amount of HCl decreases due to the reaction, right? You put base in there, it reacts, and you get some functional dilution due to this change in volume that comes from adding in all of the solvent that carried the base. So importantly, if we want to now go back to pH, we want the concentration of hydroniums. Because HCl is a strong acid, that means the concentration of hydroniums after it reacts is going to be equal to that concentration of HCl that we prepared it to be, or that it functionally would be, kind of measured as. So it's 0.093 molar. So that's one of the nice things about strong acids. So that means the pH is negative log of 0.093. So that means the pH is equal to 1.03. So a lot of work, but we can finally get our answer. And so there are a lot of steps, but one of the things to note is that because we are dealing with strong acids and strong bases, we can make our lives easier at a lot of these steps because we can use stoichiometry here. This is kind of looks like an ice table, but this was it, right? It was just it's just a way to set up limiting reagent problems that works with acid-base chemistry that kind of mimics the ice table format, but you don't have to then solve an algebra problem, which is always very nice. Then once you figure out the HCl concentration, because it's strong, again, the hydronium concentration is just equal to that nominal concentration of HCl. So you can just take that, plug it into the pH, and you're just done. And so that's one of the things that's really nice about strong acids and bases, which is why we use them so frequently in titrations. It doesn't necessarily decrease the steps, but if we were using a weak acid, we wouldn't have any fewer steps here. Each step would just be more difficult, because you'd have to use equilibrium approaches for all of those steps. Nothing can be stoichiometry. So it's much easier, much preferable to use strong acids and strong bases. That's a real strong advantage, that it just simplifies the calculation. The reactions are going to be more clean. They're all going to completion, which is really what defines a strong acid. These reactions are going to completion, especially when it comes to the reaction with water in terms of determining pH.
So if we look at this point in the titration, we started with a nominal concentration of 0.2. We are now at a concentration of 0.093, so barely a little lower than 0.1, which means we're about halfway done with this titration. We're about halfway to the equivalence point in terms of diluting this thing, getting rid of the HCl, but we can see that the pH has barely changed. Okay, so the concentration of HCl has fallen by about half, but the pH hasn't really changed much at all. And this is because the pH is a log system. And so in titrations, pH is really slow to change as you add base. It doesn't really change much because in order to change by a single pH unit, remember you got to change the acidity by a factor of 10. So you would have to affect the concentration of HCl by a factor of 10. Functionally, this makes the pH curve for a titration look like an S. As you start to add your base, the pH does not change very much. It does go up. The pH will constantly be increasing in a titration. You're adding base, the pH should increase. Then once you get close to the equivalence point, there is a sharp and large jump in the pH at that equivalence point. And then it flattens back out and doesn't change much as you add more and more base to your solution. So this jump right here is what we are talking about with a sharp change in the properties of the solution near the equivalence point. If you have, say, this indicator molecule, it is, say, colorless in acidic solutions and then pink in basic solutions, you would have a really big change in pH right near the equivalence point that causes pretty drastic changes in the properties of the solution. All of a sudden you go from like a pH of 3 to you add 1 more milliliter of base, and then all of a sudden the pH is 11. It's a huge jump that happens over a really short, really small window of base volume added. That does make titrations very tricky to get right at the equivalence point, but there certainly is going to be a very sizable change in the acid-base properties of the solution. And this really does have to, because pH is a logarithmic scale, you have to change by a factor of 10 in order to get the pH to change by 1 unit. So you need to get 90% of the acid to be consumed in order to see the pH increase by 1. And that's pretty close to the equivalence point, right? And then you're looking to see, that would mean the pH goes from like a pH 1 to pH 2. You need to get to pH 7. So, you need to get down to, 0.00001% of the acid entirely gone. And so it really does have a very short window where you start to see those pH changes. And one of the things we can also see then is as you're adding this base, you are really kind of drive the reactions of what's going on. It's a strong acid reacting with a strong base, and it really is the strong acid is going to be, hydroniums, strong bases make hydroxides. And so you can kind of parse out the relative properties of the solution really do change that initially you have it's acidic, right? You have more hydroniums than hydroxides. At the equivalence point, you have that equivalence of hydroniums and hydroxides. It's a neutral solution. And then at the end, after that, you have more base. It is a basic solution. You have more hydroxides. And again, that's kind of the drastic change right at that equivalence point. And so, the titrations always have this strong S-shaped curve. If you did a titration of a strong base with a strong acid or vice versa, it's always going to look the same, and the equivalence point will always have a pH of 7. So it's hard to find right at the equivalence point, right when pH is equal to 7, but it is common to see that big jump. That big jump is how you know you've reached the equivalence point. And even if you're off, you're at the end of the jump versus the beginning of the jump in pH, that's like a 1 milliliter difference. And so say you were doing the titration of, say, 0.2 molar NaOH with HCl, now you would monitor your progress as volume of acid added. And so the only difference is that you start with a high pH and you decrease, right? You start at a high pH, say 13, and then you are slowly decreasing, it's still pretty flat until you hit that equivalence point, and then it's right at the pH equals 7 for that equivalence point. It's always 7 because it's a strong acid and a strong base. Don't worry, we'll circle back with what happens for weak acids and bases. But for now, 7 for strong acid, strong base. Okay, no participation questions in this video, but 2 more left. There's one last topic, 2 videos, 1 topic, structure-city relations. That'll be the end of chapter 14 for us. Well, see if any more questions for the participation assignment are in those videos. I'll see you there. Bye-bye.